So welcome you guys to the lecture number 1 for the rocket propulsion. As I told you in the last class, I am going to start a new subject in the next lecture. So today I am going to start the rocket propulsion, and there are basically 3 chapters in the rocket propulsion. One by one we'll see. And my name is Ujjwal Srivastava. I am doing my master from IIT Kanpur, and these lectures are dedicatedly for the GATE 2026. And here I have given my number so that if you need any guidance or any help from my side, you always contact me on this number. You can WhatsApp me, you can call me anytime. I'm free for you always. And guys, one thing I'm getting notice, the peoples are coming to this channel and watching the videos, and they did not subscribe the channel. So please subscribe the channel because it will be help you, and please share with your colleagues and juniors and seniors, whoever needs this video. So let's start the class. So there are basically 3 chapter in the, you can say, rocket propulsion. So let me take. So the first one is a rocket. Okay, let's do not all this. Let's start the class basically. Right, first chapter as you can, right, first chapter, right, first chapter as efficiency of propulsion system. First chapter as a efficiency of propulsion system. Let's see. Chapter first is efficiency of propulsion system. So we'll see the efficiency for the propulsion system is, it can be your air breathing engine, that means your jet engines or whatever is flying under the atmosphere, or it can be your non-air breathing engine, that means a rocket engine. So now we'll not go into depth for the rocket engines, but of course we'll go to the depth for the air breathing engines. We'll see all this component of the engines in the air breathing when we'll do the jet propulsion. But as of now, we'll see the rocket propulsion. And in rocket propulsion, there is no any rotating component, compressor turbine is not there, but still we're not going to study the rocket engines, right? So right, first you write what is efficiency. Right, first topic as efficiency. So efficiency generally means what happens when, see, how much, or you can say how well something works. One second guys. Continue. How well something works without wasting time, energy. So this is called efficiency. That means, let's suppose I'm giving you example. Let's take an example over here. Let's suppose if one engine uses 10 liter of fuel to go 100 kilometer, this can be your first scenario, right? And the second scenario is the second engine, it can be any engine, uses 5 liter for same distance. That means what? It means your second engine is efficient, it is burning less fuel than the first one, so it is called basically efficiency, right? Then after propulsive system, we have already told you there are two types of propulsion system: air-breathing engine or non-air-breathing engine. So in air-breathing engine, we'll do in jet propulsion whatever are the component, whatever we do in engines like jet engines, turboprop, turboshaft, all these engines we will study. And in the non-air-breathing engine, we'll basically focus the you can say the propulsion system of the rocket engine. Will not go depth into rocket engine, but still we'll study sometimes. So now you write one term which will come often. Let's suppose this is your black box. So what is black box? Because we are going to assume all the propulsion system as a black box, because the reason is, see, I'm going to give, see, it is system where we only focus on input and output, right? Not interested and not worrying, you can say, about inside. Okay. Let's suppose I'm giving you an example. Suppose this is your gas turbine engine, right? Suppose here is a compressor. All these things we'll study when we will do the jet propulsion in very depth. Suppose this is your turbine. This is a diffuser, compressor, combustion chamber, turbine, and nozzle. There might be your afterburner or something. We'll see when jet turbine. Fine. So here we are basically focusing how the air is coming inside this engine and how it is going. We are not focusing about this, or not worrying about this. We are not interested. So only we are interested as a input and output. So that is basically called a black box. Why it is? To simplify the problems. To simplifies analysis. Right. We are about okay, leave it. Only it. For simplify the problems, basically we use black box. Now you write. Now let's start the the main operation, the main content from here. Right. The propulsive system is treated as black box. I told you already why you treat it as the black box, right? Now you write, I'm going to draw two figures. See, then the figure A and figure B. Fine. Below show the specific feature of such system for air breathing engine and non-air breathing engine. I'm telling you why I'm calling it air breathing and why I'm calling it non-air breathing. I will tell you in a while. Fine, right. Draw the figure. Suppose you are not worrying about the you can say the internal part, so we can say this as a black box, or you can say the propulsion system. So you can say the propulsive system, right? First we see, I am calling it the air breathing engine. This is your air breathing engine. So let's suppose your airplane is going in this direction. That means it is having the some flight speed. So VA is nothing but your flight velocity of vehicle. Fine. So it is going in this direction, obviously. In this direction, right? So in our aircraft engine, or you can say the air breathing engine, whenever the airplanes goes, let's suppose the airplane is going like this, so it is sucking the air by the compressor, or you can say by the diffuser. So it is sucking the air basically. So air is coming inside the your engine, right? So mass flow rate of air is given. This is called mass flow rate of air. That means how much mass of air is coming per second. Rate of air, right? Similarly, the air is coming inside your diffuser, but we know that we inject some fuel in our combustion chamber, right? And some heat we have to generate. All these things, how we are giving the fuel, and how we are injecting the fuel, and how we spark it, and how we get the you can say energy. All these things we'll study in jet propulsion. Let's suppose as of now you assume the air is coming into the engine, and in the combustion chamber, this is basically called oxidizer, you can say oxidizer, right? And this is basically your fuel. So in our combustion chamber, basically you use this oxidizer and this fuel, and we spark it for the combustion. Basically combustion is nothing but your you can say the fire, you can say. So using these two, we generate the combustion, and we fire the fuel and all. Then we get the heat in the form of energy, right? And that energy we extract from the turbine, and we get the thrust. Basically that is the main idea from here. And but we'll discuss in the jet turbine or jet propulsion, you can say. So if you are getting this mass flow rate of air, and if you're injecting this fuel, so at the end of the, you can say, nozzle, you will get the combination of both. That means mass flow rate of fuel plus mass flow rate of air, and that is basically called as M of A. That means the mass flow rate of exit. Mass flow rate at exit. This is a combination of both mass flow rate of a fuel plus mass flow rate of air. Fine. Okay. So that is why it is sucking the air. It is sucking the air, and this aircraft system, or you can say the engine, is running using this air. That is why we are calling this air breathing engine. Fine. Now you understand the rocket engines. Now you draw again. Let's suppose this is your figure A. Fine. Now you draw a propulsion system. suppose your rocket is going in this direction, so it is having some velocity. That velocity we can say it a VA. This is a flight velocity, right? You can say flight speed velocity, or you can say the vehicle velocity, you can say free stream velocity also you can say when you will study the aerodynamics or something. So we as of now call it as a flight speed or flight velocity, you can say, right? Here what we can say it, in a space there is no any air, so mass flow rate of air is 0. That means no mass flow rate of air is going inside the engine of rocket. Fine. So it is basically 0. Fine. But in the our combustion chamber of rocket, we use fuel plus oxidizer together. That means we have to carry fuel as well as the oxidizer to combustion, right? So fuel and oxidizer we are having in our combustion chamber. There is no any air from our atmosphere, that it is calling as a non-air breathing engine. Non-air breathing engine, right? But still we are having the exhaust velocity, or you can say exhaust velocity as well as you can have the exhaust velocity from here also. Exhaust velocity as well as the mass flow rate of exhaust, right? You can say. So these are the basically combination of the fuel and oxidizer basically, but there is no any air, so you can basically say the mass of fuel as your m of E. Fine. So this is basically funda of non-breathing engine or air breathing engine. Let's say this is your figure 2, or you can say figure B. Fine. Okay, let's go ahead. Now I'm going to give you one formula that is for the air breathing engine. Let me write. Right. The expression for thrust, I'm giving it for the thrust basically. So okay, let me draw one figure so that you can understand very neatly what is thrust and all these things. So this is your aircraft. Fine. So there is something called as CG. What all these things we will study in a flight mechanics. What is CG? What is the lift and all these things. So over this CG we are having the one force that is called a lift, which helps to lift the airplane upward, right? To balance this lift we are having the weight of an aircraft, or basically we can say to balance this weight we are having the lift. Similarly, the airplane is going in a forward direction, so it is having some velocity, or it is having some force. So that force we call it as a thrust force, right? Basically which is used to balance this drag. So basically this is the main funda of a airplane. There are basically 4 forces which you have to balance to each other. So basically that is why, let me take, okay, so now I'm talking about this thrust here. Thrust of an, now right, of an air breathing engine. That means I'm talking about the aircraft, not breathing, so air breathing engine. So this is your, I'm calling it F, or you can say the T, no issue. So see, mass flow rate of air plus mass flow rate of a fuel into velocity of fuel, not velocity, velocity of at exit minus mass flow rate of air into velocity at entry plus area, cross-sectional area at exit into PE minus PA, that is the pressure at exit into minus pressure at inlet. So let me take this over here. Fine. All let me draw this here, plus AE P minus PA. Let me draw this. Fine. So this is expression for the thrust for the air breathing engine. Fine. Let me told you this part is called as the momentum thrust. Momentum thrust, and this part is called as the pressure thrust. So in the the thrust equal to momentum thrust plus pressure thrust. So basically it is the combination of both the thrust, right? It is combination of both the thrust. So this formula, whatever I have written here, we are not going to drive here. We will drive this formula when we will do the jet propulsion in very neatly and very clearly with all the steps. So as of now, please remember this formula as a thrust for the air breathing engine, right? Now you write what are the things over here. Okay, here what is M of A? That means mass flow rate of air, right? That means how much mass is entering in the engine per second, right? That is why we are dealing with the flow rate. Fine. Similarly, what is M of A? That means mass flow rate of fuel. That means how much fuel you are injecting from your combustion chamber. I mean how much fuel you are injecting to your combustion chamber per second. Fine. Okay. This MA plus MF is also called as the ME. So you can remember this ME is equal to MA plus MF, or you can say from here you can also write this as a M of E. That means mass flow rate at exit. So what is a M dot E? It is a mass flow rate of exit, right? Means from nozzle how much mass is getting out per second. That is the mass flow rate of exit. Fine. Now write one another term. What is VA? This is the flight speed of that particular vehicle. It can be a rocket, it can be an aircraft, it can be anything, right? Then after we are having the VE. It is the flight speed of vehicle, you can say at entry to at exit. That is why I am writing E. Fine. What is EE? A is nothing but your cross-sectional area of nozzle. Fine. Once again, guys. Now this A is happening. Okay. What is this PE? It is the pressure at exit of your nozzle. All these things we'll study in very depth. What is nozzle, what is all these things. So don't worry. As of now, please remember all these things. What is PA? So it is the pressure at entry of your vehicle. Fine. All these things we have. Okay, right? Now right. Let's suppose there is something called expression for the over-expanded organism. Okay, fine. So now for rocket engine, we know the mass flow rate of air is 0. So we can write this formula as now F is equal to mass flow rate of E into velocity at E minus 0 plus AA into P minus PA. Fine. That is equal to your m dot VA plus AA into P minus PA. How am I writing this? Let me explain. Right? As I told you, the mass flow rate of air in a rocket engine is 0. That means this term is getting 0. So only we are left out this term and this term. Fine. This term is written over there, and this I am written as a mass flow rate of an exit or mass flow rate of a fuel. You can write this. Right. That is why I have written all this formula. So let me take the naming for, or you can say equation number. Let me take this is the equation number 1, and this is as equation number 2. So basically this is for rocket engine, you can say, right? Now let me simplify more. So we know that one of the classical design condition for rocket nozzle is PA is equal to PA. Fine. That means the exit plane pressure, or you can say the exit pressure of nozzle, is exactly equal to the atmospheric pressure, or you can say the pressure around your rocket. So if that is equal, that condition is called an expansion. You can say the optimum. These things we will study in the gas dynamics in very depth. This what is optimum expansion, or what is the P and P, all these things we'll study in the depth. So as of now, please remember only one condition. If the P equal to PA, that is called the optimum or adapted condition, or adapted. And I will show you if this is equal to this one, so what happens and how the exhaust gases comes from the nozzle exit. Adapted condition. Right. So now if I will apply this here, so you will get as F equal to m dot VP. Fine. So this basically, this is rocket engine equation for adapted condition. Right? You can remember this formula. In the question, if they ask any in the question, if they ask, and if they want to use this optimum or adapted condition, so they will definitely tell you the optimum condition or adapted condition, or you can say the perfect expansion. Perfect expansion. Right? Now I'm going to draw one figure which is very useful. Please draw it. Please draw it very neatly. Suppose this is your. It is very important for the efficiency, basically. Suppose this is your boundary. From here to here, suppose this is your A. This is nothing but your, let me tell you, the total input power, or you can say the fuel energy. Fine, that is equal to m dot of the fuel into qf. This m dot of fuel, I already told you, mass per unit of a fuel. This qf, let me tell you, this is your calorific value. That means when we burn 1 kg of fuel and heat is released, or you can say generated, that is called as calorific value. That means when you are burning the fuel 1 kg in the combustion chamber, that means from that, if the heat is released, so that heat is in the form of energy, so that heat we use as extract the energy from our turbine and all that. I already told you, so that is called as a calorific value. Fine. Now if you you can say, if you burn the fuel, there might be the unavailable energy. So let's suppose from here you are having the unavailable energy. What does it mean? Let me tell you. Unavailable energy. So let me define what is this unavailable energy. So it is part of input energy. That means whatever you are giving by burning the fuel, that cannot be used to produce thrust. So it wasted due to physical reason. What can be the reason for wasting this? It can be reason as a fast exhaust gases, then friction, heat loss, etc. Fine. So this is your called here unavailable energy. Fine. The second one, let me take as a, okay, it will be a little bit, okay. The second one, let's suppose this is your B. This is your kinetic power. Fine. From here also there is going to be losses. Why it happens these losses? Let me tell you. Let me take another one. Okay, let me take the yellow. Yeah. Why these losses happens? Let's see. You can say after the air fuel burning by mixture, and accelerate. Obviously when the fuel and air will be mixed and burned, then the mass flow rate, you can say mass flow rate of vehicles will increase. That renders to the thrust of the vehicle, and that renders to the flight velocity. So it will be increased or it will be accelerated. Some energy remain in the fast moving exhaust gases. I will tell you once again all these things. Let me write exhaust gases. So it is not recovered. So it is loss. It's a loss. And it is not recovered. That means it is unutilized. Unutilized gases. Fine. So now let me tell you what I'm saying from that time. See, this is your energy you are giving your input by burning your fuel. Fine. So there is some fuels which basically don't burn. So it is a part of the input energy that cannot be used to produce the thrust. That means that is not burning actually. So it is wasted. It can be reason fast exhaust velocity, or you can say the fast exhaust gases. If you burn the fuel, then the flight speed will be increased. That means the exhaust gases that will come from your nozzle will be very fast. So there might be fuel which basically cannot burn. They don't have that much time to burn. So that is called an unburned particles or unburned carbon, you can say, or unburned fuel, you can say. So that is the first reason, right? Second reason is what is the losses in the your jet. So when the air fuel mixture happen, the burning will be happen, of course. So it will be accelerated because this burning will give you the energy, and that energy is extracted by your some component in rocket. So the flight speed will be increased, which renders to the first exhaust velocity. So first exhaust velocity means there are some particles or some fuel which basically not burn. So that is our loss. That will not recover. So it will go out of your nozzle. So that will not burn. So that is called your loss. And that is also called your unutilized gases. Because we are unutilized gases, unutilized fuel, unutilized kinetic energy, we can say, right? So that is basically funda. Now you see the third one. This is your C, and this is basically your propulsive power, you can say. Although you don't remember this graph, or you can say the figure, you no need to remember all these things, but still you have to understand what is basically losses and what is the unavailable energy. So this is basically the kinetic energy is basically 1/2 mass flow rate of a fuel velocity of exit minus 1/2 mass flow rate of air velocity of air. Fine. Now propulsive power is nothing but your F is equal to not F, P. P is equal to your thrust into the flight velocity. This is the propulsive power. Fine. Now you write formula for air breathing engine. So now we are going to separate air breathing engine and the rocket engine. So first we will find the propulsive efficiency for the air breathing engine. That means your turbine engine or gas turbine engine. Then after we will go for the rocket engine. So first you write the air breathing engine. Right. So as you know that F is equal to mass flow rate of air, mass flow rate of a fuel into BA minus VA into VA plus AE into P minus PA. So that term is called as the momentum thrust. That term is called as the pressure thrust. So now let me take condition. If PA is equal to PA, there is a perfect expansion condition we are taking. So what happens? This F becomes MA plus MF into VA minus MA into VA. Fine. Okay. So let me take the equation number 3. Now what happens? Let me take this A as a common. So F is equal to mass product of A. Let me take as a common. So 1 plus M mass product of fuel divided by the mass product of air into VE minus mass product of air into VA. Fine. Oh sorry, this will not come. We have to take this also. Fine. Now see. This mass product of fuel divided by mass product of air is something called as a F, that is your fuel to air ratio. Fine. Sometimes it can become for your 1 mark. So if they can give you the mass product of fuel and they give you mass product of air, they can find fuel to air ratio. They can give the fuel to air ratio. In all these 3, they can give you 2, and you have to find the third one. So you can also expect one question from this for 1 mark. Now write. So F is equal to mass product of air is equal to 1 plus a small f into VA minus VA. Let's suppose this fuel to air ratio is very, very low. Let me take, if this F is very, very low, so the above equation we can write as, if it is very, very low, that means less than very 1, that means it's F equal to 0. So you can write the F is equal to MA into V minus VA. So this is your question number 4. Fine. But for applying this equation, you need to remember the condition. What is the condition? Why? The conditions is first is a optimum condition. Optimum means perfect expansion, okay, or adapted condition. Optimum condition, that is your PE is equal to PA. Fine. And the second one is the fuel to air ratio is less, very, very less. Fine. So if these 2 conditions are given in your question, then you can write directly this formula. So I'm recommending you to remember always this formula, or you can say this formula, so you can drive all these things, whatever we are doing now. Fine. So now write the propulsive efficiency. Right? The propulsive efficiency, obviously for air breathing engine. So right, the propulsive efficiency is nothing but your, or you can say the first you can write the what is the efficiency. Efficiency nothing but your output divided by input, and output divided by output plus losses. This is your efficiency. Fine. Now you write the propulsive efficiency. So NP of air breathing engine is nothing but your, see this, I'm taking as a propulsive efficiency of air breathing engine as a C by B. That means this propulsive power, that means this propulsive power divided by the kinetic power. Fine. To write, this is your C by B. Let's see nothing but your propulsive power. Because the propulsive thrust power, because thrust is there, that is the thrust power we are calling. Then output net, that means propulsive thrust power plus unutilized kinetic energy, that is your unutilized, that means losses is talking about. Fine. So propulsive power is nothing but your F into velocity of flight velocity, you can say, into F into VA. This F is nothing but your thrust plus half m dot V minus V to the whole square. Now what to do is, this can be written as mass flow rate of air into V minus BA. This can be written as like this from here, right? Equation 4. Now again VA, still mass flow rate of air VA minus VA into VA plus, now you write, see, m mass flow rate of fuel is very less than the mass flow rate of air. So mass flow rate of a fuel plus mass flow rate of air can be treated as mass flow rate of air, right? So that is why I am writing half of mass flow rate of air into V minus V to the whole square. Fine. So cancel out these things. Mass flow rate of air gone, A gone, this one gone, this one, and this one gone. So we will have VA divided by VA plus half V minus VA, right? Now this can be written as 2VA divided by 2VA plus V minus VA, which is nothing but your 2VA divided by VA plus VA, right? You can write this. So I'm writing one term that is called as the alpha, which is nothing but your VA by VA. It is called as the flight speed ratio. Alpha is nothing but your flight speed ratio, you can say, or flight speed you can say, right? So now you write, so the propulsive efficiency for air breathing engine is nothing but your 2VA divided by V plus VA. If you take this one in terms of this one, how you will see this? Let's suppose, or you can say, okay, you can divide by, see, this equation we can divide by VE, so you can get in terms of the alpha. So if you divide by VE, this is nothing but your VA by VE divided by VA by VE plus 1. So propulsive efficiency nothing but your of your A is nothing but your 2VA divided by VA plus VE, or you can say 2 alpha divided by alpha plus 1 plus alpha, you can say. This is your equation number 5. So in question, or you can say in exam question, there are multiple questions in which they basically give you the VA, VE, and they ask what is the flight to speed ratio as well as what is the propulsive efficiency. Or you can say they can give directly flight to speed ratio alpha, and they can ask directly what is the N of V. Fine. So let me finish over here. I'm going to upload next lecture after 2 or 3 days. So study till here and I will continue from next class. And thank you so much for having patience with me. And please subscribe my channel and share to your juniors, seniors and colleges, because there are many students who come and study and they did not subscribe. If you subscribe my channel, so you will get benefits of course. And please feel free to share with your friends. This is my contact number. You can always contact me on this number whenever you need something help from my side. So please have patience and stay with me. We'll finish the gate syllabus, whole gate syllabus, and we'll crack the gate in 26 for sure. Thank you so much for having patience. Let me continue with the next class. Thank you so much.